तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello, welcome to the National Program on Technology Enhanced Learning. This is a program funded by the Ministry of Human Resource Development for the benefit of engineering students in the country. What we propose to do here in this program is to provide you a series of lectures on various topics, and I am here to give you a series of lectures on the basic chemistry, the first year core chemistry curriculum that most engineering students should be familiar with in order to appreciate the fundamentals as well as the role of such fundamental ideas in engineering applications. So the purpose here is to introduce you to basic principles of chemistry. Okay. Let me introduce myself. Okay. I am MangalaSunder. I teach in the Department of Chemistry, Indian Institute of Technology, Madras in Chennai. The address for electronic mail communication to me is mangal@iitm.ac.in. Okay. Now, the core chemistry curriculum that we are interested in giving you in the form of lectures concerns with the principles of chemistry and not necessarily the applications of chemistry in engineering. Okay. It is our sincere opinion that the applications in chemistry in engineering are best taught by the respective specialized engineers. The basic ideas in chemistry, as the chemists understand, as the fundamental scientists understand, as are relevant for the engineering principles, applications, etc., they are of interest to us. Therefore, this series of lectures, let me give you the sequence of the lectures in chemistry. The first 12 to 15 lectures will be on atoms and molecules. This is essentially the basic quantum chemistry that we should be familiar with. This will be followed by a series of lectures on molecular spectroscopy. It is a fundamentally important subject for all of chemistry, physics, engineering, biological sciences, whatnot. The applications of spectroscopy, the applications of detection techniques, everything is described in detail in molecular spectroscopy. Of course, I would not do all of that, but introduce you to the basic principles of spectroscopy. There will be a few lectures on solid state chemistry, electrochemistry, approximately 3 to 5 lectures, and elementary chemical reaction kinetics and dynamics. Again, some 10 to 12 lectures, followed by surface chemistry, approximately 3 to 5 lectures. This is the organization of the series of lectures that I propose to give on the engineering chemistry course of the NPTEL project. We will start with the first and most important aspect of chemistry, namely the constituents of chemical systems, the atoms. there are obviously 114 types of atoms that we have, and the mechanics of the atoms. The mechanics of the atoms when they are together, the interactions between the atoms to form molecules, etc., are fundamental to what one calls as chemical transformations. So the first module is on the atoms and molecules. What do we propose to do in this atoms and molecules lecture? We will basically look at the elementary quantum mechanics as applied to chemical systems, or as is done in chemistry courses. An elementary survey of the principles of quantum mechanics, as well as some introduction to simple models. These are of interest to us in understanding the atomic structure, and consequently from the atomic structure how the atoms form molecules, and therefore the molecular structure. Quantum mechanics is of course fundamentally important subject. This series of lectures will only give you what are called the prescriptions of quantum mechanics. This is not a place, nor do I have the expertise to tell you that at the end of this you will understand quantum mechanics. In fact, nobody does. Therefore, when we talk about the importance of quantum mechanics or the importance of quantum chemistry, what I would focus my attention are the methods by which we apply the rules of quantum mechanics. If you ask me how we get to these rules, I am not in a position to explain them in detail here, nor is it the purpose of this course. This course is to understand the rules as they are and manipulate the rules to follow how molecules form in some elementary manner. The principles of quantum mechanics, I will only list them as principles without any discussion on how they were arrived at. The only way to become familiar with quantum mechanics is not by asking the question, how do I understand quantum mechanics, but by asking and trying to answer the question, how do I use the methods of quantum mechanics as prescribed in the textbooks or as prescribed by the founding fathers of the subject. Okay. What are the methods? What are the principles that I should apply? Let me not question the principle. How do I apply? How do I become familiar? And later on in the process of continuous education, let me try and understand why these principles arose the way they are now. Okay. So it is not about understanding quantum mechanics, but it is about becoming operational in using the algebraic procedure in quantum mechanics. Why is quantum chemistry extremely important in chemistry? Quantum mechanics is important in chemistry. It is the basis of of the understanding of chemical bonding at the molecular level. Okay. As you see here, it is the basis for understanding the molecular interactions. Quantum chemistry provides, let me repeat, the basis for understanding chemical bonding. Why molecules form, why molecules disintegrate, why molecules dissociate, rearrange, basic ideas of the formation, rearrangement, dissociation of molecules. The basis of understanding is of course in quantum chemistry. Also the interactions between molecules which are responsible for chemical reactions, which are responsible for physical transformations, all these things are also from the principles of quantum chemistry. And most importantly for a practical chemist, the quantum chemistry provides the basis for understanding the interactions of molecules with electromagnetic radiation. This is the branch of spectroscopy. Spectroscopy is how we detect, we determine, quantitatively assess various chemical species, intermediates in a chemical reaction, and many other things. So an important aspect of molecular spectroscopy, the basic theory is provided by the methods of quantum mechanics and the methods of quantum chemistry. Okay. Now let me summarize how we got to where we are today. Okay. That is, we are summarizing the effects of a little more than 100 years, 105, 106 years to be exact. In 1900, Max Planck proposed a relation for the energy released by the material body at high temperatures. Max Planck was studying a certain phenomenon called black body radiation. The phenomenon could not be understood in complete form by the methods of classical mechanics, the Newtonian mechanics, classical electromagnetism. Max Planck came up with a radical suggestion that the energy released by the material body, as it is raised to very high temperatures, the energy is released in the form of light, in the form of radiation. The energy is released in packets from the material body, and he defined the size of this packet by the relation here. The energy associated with the material bodies, the energy packets which appeared, is a constant times the frequency of the radiation. E is equal to h nu, the first relation proposed by Max Planck, where h subsequently was called Planck's constant. And if you look at the value of Planck's constant, it is an extremely small quantity, 6.626 times 10 raised to minus 34 joule second. Planck's constant has the dimensions of energy into time, frequency has the dimensions of 1 by time, therefore this is energy, and the discreteness in the energy that is being released, the discreteness is so small, as you see it, the number h is so small that we probably did not know until then that energy is coming from the hot body in packets, but we thought it was a continuous radiation. Max Planck proposed this as a hypothesis and was able to explain the phenomenon of black body radiation completely. It was a proposal, it was a hypothesis, but most importantly he introduced a constant which bears his name to this day. This is the first phenomenon in which the idea of a quantum of energy was introduced. 5 years later, Albert Einstein, who was very young at the time, came up with a brilliant explanation of one of the unsolved problems in physics at the time for a phenomenon known as the photoelectric effect. Albert Einstein, in that year, we celebrated 101st year now from those, that is, it was 1905. So this year is 101 years since Albert Einstein published 3 most important papers in all of physics and in all of science. In one of the papers describing the effect known as the photoelectric effect, Einstein came up with an explanation, and in summary what he said was that light or the electromagnetic radiation itself consists of packets of energy. There is no other scientist in the world that I know of whose work was never questioned for the award of Nobel Prizes. Everybody thought Albert Einstein should win the Nobel Prize. The Nobel Committee had no doubts that it should give a prize to Einstein. The only question was which of the 3 papers that he published in 1905 should be given a recognition for the Nobel Prize. One was photoelectric effect, the other was his radical revolutionary idea, that is the theory of special relativity, for which he drew substantial guidance from other physicists, most importantly Lorentz. And the third paper that Einstein published in that year was on Brownian motion. we will not worry about that. I mean, all of us know that Einstein was probably the greatest physicist ever to have lived in the last century. His idea that light itself consists of packets of energy, we call them as photons today. Einstein did not call them as photons, but I believe it was a chemist, Gilbert Newton Lewis, who probably coined the name photons for the light packets later, almost some 10-15 years later. The expression that Einstein came up with for the discrete packets of energy for the electromagnetic radiation whose frequency is nu is also the same relation that Einstein gave, E is equal to h nu. And Einstein was the first to recognize that this h is exactly the same as the h of Max Planck. This was the second revolution, that the energy that is emitted by the material bodies or the energy of the electromagnetic radiation itself consists of discrete packets or quanta of energy, and the quanta or the quantum is given by h nu. Then came another important discovery. This was by Louis de Brownlee, a French physicist, a French history student turned physicist. Louis de Brownlee graduated in BA History, but in a few years he became a first-rate physicist. And de Brownlee proposed the idea that light, if it has to be particulate or if it has to behave like particles or if it has to behave like waves, it is not just light. De Brownlee proposed that all material particles moving can be treated as matter with a certain wavelength. He introduced the idea matter waves. What he suggested was that the wavelength lambda that is associated with the moving particles with a mass m and therefore a momentum p, which is mass times the velocity if the velocity is not very large. De Brownlee proposed a relation for the wavelength lambda by lambda is equal to h by p, where this h is again the same constant, the Planck's constant. So by this time people realized that there is something fundamental about h, the Planck's constant, the action constant, that it has a certain importance in physics, and of course it has a fundamental importance in chemistry through the Schrodinger equation, which we will study later. These are the three most important phenomena that I would like to highlight before moving on to the basic formulation of quantum mechanics as we know today. In a typical physics course, you will probably learn the details of how blackbody radiation phenomenon has been studied by Max Planck through all the derivations. You might also go through the derivations of photoelectric effect. In fact, if I recall the textbook for high schools, the Central Board of Secondary Education class 12 textbook describes the photoelectric effect in detail. So you must have studied them already. The matter wave is a new idea, that is all material particles which are moving with certain speeds have in them an associated wavelength. That is, we are all like waves when I start moving like this, okay? Not when I am stationary, but if I am moving there is a wavelength associated with me. These are all ideas which eventually culminated in the formulation that we know today, the formulation by the Austrian physicist Erwin Schrodinger. I am going to give you a prescription. What is a prescription? You go to a doctor with the idea that you want to cure something. The doctor gives you a medicine. Very few of you will probably ask, why should I take this medicine, why not something else? Okay. Or why should I take this medicine, 2 pills 4 times a day, why not take all the 8 pills at the same time? Okay. I'm sure you must ask these questions. And I'm also not certain that many doctors will entertain this idea. But if they do, they will explain to you the reason behind why you have to do it this way. There are principles. Of course, medicine and the cure is established on the basis of the observations, experiments, hundreds and hundreds of years now. Okay. Quantum mechanics is also, the way I give you is a prescription. I cannot explain to you why the rules are what they are. The only reason the rules are what they are is that they seem to explain practically every phenomenon that we have come to experiment with since 1926. There are 2 fundamental equations in quantum mechanics and in quantum chemistry anywhere you go when you study the microscopic systems of atomic dimensions. The 2 equations I will simply give you, not by slides, but let me write them down. In fact, there is only one fundamental equation, not 2, but the second one is derived from the first one. One fundamental equation Erwin Schrödinger proposed by him in 1926. I h by 2 pi plus I h by 2 pi, the partial derivative of a function called psi is equal to another quantity called the Hamiltonian and the same function psi. This is the most important equation of microscopic science and the one which governs the properties of matter. Everything that we know seem to have followed from the application of this. The h is the same h as the Planck's constant. There is a partial derivative with respect to time, and there is a quantity with some hat on the top. Okay. This quantity has a classical analog. It is known as the Hamiltonian, but it is written in a specific form for the mechanics of atoms and molecules. The Hamiltonian is an operator. We will come to know all these things later, but the equation that we have to remember is I h by 2 pi d psi by dt is equal to h psi, where what is I? Most important, it is square root of -1, it is imaginary. So we have an equation involving complex quantities, but you will not study all of this, but in chemistry you will only study this equation, h psi is equal to a constant times psi. The first one is known as time dependent Schrödinger equation. The second, h psi is equal to E psi, is known as time independent Schrödinger equation. Let me go back. What is h? What is psi? What is E? We will come to know all these things. In grade 6 or perhaps in grade 8, when somebody wrote this equation, f is equal to ma. We all understood, or we all solved the equation, we studied the equation, and we said this is Newton's second law. For the motion of objects of macroscopic size, objects of planetary nature, very large scale. Force is mass times acceleration. That is not the meaning of this equation, that is just the words of the mathematical symbols. We never questioned what is F or what is ma. We understood, yes, this is the equation that we have to solve in order to understand the dynamics of particles, dynamics of things that we observe. Schrodinger came up with this idea that the dynamics of atoms and molecules, or any objects which we cannot see in microscopic dimensions, has to be understood by solving an equation which looks like this: I h by 2 pi d psi by dt is equal to h psi. Okay. Now, do we understand this? If you ask me, I do not understand this, but obviously I know how to solve this equation for certain problems. And one never tries to understand quantum mechanics at the first time, quantum chemistry at the first time one learns, but works with the basic methods, tries to solve problems, analyze the results of the problems, find out what is new in the solutions of the problems as different from the solutions that one would get if one were to use classical methods, and sees that the quantum systems give you the answers which are actually observed in experiments. Most important experiment is spectroscopic experiments. So this is a prescription. We are going to go with this. We are going to try and understand how to solve h psi is equal to E psi. The entire atoms and molecules module is on the solution of this equation for various forms of the Hamiltonian. The corresponding solutions are all known as wave functions. This is a wave equation, and the quantity E are known as the energies that one can observe if one tries to measure the energy of the system under study. These are the possible energies, and the entire exercise of quantum chemistry is to determine the wave functions and the energies through the solution of an equation called the time independent Schrodinger equation, where the h is the Hamiltonian. The Hamiltonian is not a quantum quantity, it is a classical mechanical quantity representing the total energy of the system. Kinetic energy plus the potential energy of a system is what is known as Hamiltonian, in honor of Sir William Rowan Hamilton, physicist in the 19th century. But the Hamiltonian will be written in a special form for quantum mechanical problems, and therefore will require methods which are different from the methods of classical mechanics. Okay. As I said earlier, h is the Hamiltonian of the system, or the Hamiltonian of whatever things that we want to study. Hamiltonian is nothing but the total energy of the system. The total energy of a classical system is obviously given by the kinetic energy and the potential energy. You know, for a particle moving with a momentum p, if the particle has a mass m, you know its kinetic energy, its expression is given by p square by 2m. The potential energy, for example, for a particle moving in the earth's surface, if there are no other forces, electric fields or anything else, the potential energy is due to the height of the particle from the surface of the earth and due to the gravitational attraction of the particle with the earth. Very simple. The sum of the potential energy and the kinetic energy is known as Hamiltonian, but in quantum systems we are going to replace the classical expressions or the classical mechanical expressions by replacing the momentum p in a unique way. Momentum is a vector, and if we represent the vector in a certain direction, the component of the vector in that direction, for example along the x axis, we write the momentum as the component as px. The quantum mechanical quantity for px will not be the px itself, but will be given by this strange quantity minus I h by 2 pi h bar, partial derivative dou by dou x. If the momentum is about a certain direction with the angle, changing angle as the unit vector, the momentum is given by minus I h bar dou by dou theta. That is, what you see here is that the momentum will be not written as p, but it will be written in terms of the derivative of the coordinates used to define the classical momentum vector. Here the coordinate used is x, here the coordinate used is theta, so two things, but a derivative is an operator. A derivative has to act on a function to give you something. A derivative by itself does not have a meaning. So the result of this is that the Hamiltonian is not the classical quantity of sum of energies of kinetics and potential energies alone, but in addition the Hamiltonian becomes an operator. Psi, the mysterious quantity, okay, the one which troubled many physicists, the one which was in fact misinterpreted by its founder himself, okay, wave function. What was the meaning of the wave function? A lot of people had difficulty understanding what the wave function was. It is a wave function associated with whatever system that you study. It depends on all the coordinates available to the system. Suppose a system is moving in only one dimension, or accessible positions in only one dimension. System can be found here, here, here in one dimension. If you do that, then the coordinates available to the system is a one dimensional coordinate called the x, which you represent by an axis and the values of x as the positions. But if the system is accessing a planar area, for example, then there are two coordinates associated with that. So the system depends on all the coordinates that define the region of space accessible to the system. It is a complex, it can be a complex function. After all, you have a square root of minus 1 appearing in the original Schrodinger equation. And the most important thing is, after working very hard with all the solutions of the Schrodinger equation, wave functions, etc., you will realize, you will also be told that the wave function does not have a physical meaning, it does not have a physical interpretation. Then you will ask the question, why do I study all these things? You are telling me to solve an equation which I don't know. You are telling me to solve an equation whose solution I don't know how to interpret. Then what is the purpose of all of this? Fortunately, there were intelligent people ahead of us who did not worry about the wave function as is, as a complex function, but the absolute square of the wave function, psi square d tau. Let me go back to my notes. When you solve this, h psi is equal to E psi, psi does not have a meaning, does not necessarily have a physical interpretation, physical meaning or interpretation. So why go through the trouble? Fortunately, if psi is complex, then its complex conjugate is psi star. Okay, you know what is a complex conjugate? If a complex number z is written as A plus IB, where A is real, B is real and I is square root of minus 1, you know what is a Z star? Z star is A minus IB, that is wherever you have I, you replace I by the minus I to get the complex conjugate. What is its role? Its role is in defining Z star, or the absolute value of Z squared, which if you do the simple multiplication A plus IB times A minus IB, you get a real number A square plus B square. The IBs and minus IBs will cancel. Okay. So even when you have a complex quantity, you can define a real number from the complex quantity in terms of the absolute square of the complex number. And what is the relevance of this? The relevance of this is that if psi is a complex function, its complex conjugate psi star is such that the absolute value of psi square in a small interval of space has a meaning. This meaning was given by another famous physicist, Max Born, another German physicist. What is the interpretation? The physical interpretation is that the absolute square of psi represents the probability of finding the system in a small space d tau. D tau is a small space. For example, we will see some of the models like particle in a box, the harmonic oscillator, the hydrogen atom, the molecular problem. We will define what the space means, what a small interval of space means. All these things we will define as we go through it, but we have to understand, or we have to remember, sorry, not understand, we have to remember that the absolute square of psi times d tau, that is, you evaluate the function psi in a small interval of time, interval of space d tau, the psi star d tau represents the probability of finding the system in a small space. This is the only meaning that can be ascribed to the solution of the Schrodinger equation. The next important fact which we have to pay attention to is the quantity E in H psi is equal to E psi. E stands for energy. You know, Hamiltonian represents the total energy of the system, therefore whatever is the dimension of psi, E must have the dimensions of energy. E represents possible solutions for the energy. What does that mean? It means that when you make a measurement for the energy of the system, you will get some value, experimental values. What Schrodinger equation tells you is that the theory predicts certain values as the only possible values in the experimental measurement. It is strange that when you make a measurement of an energy of a particle that is moving in a box, why should you get only specific values? Why not any energies? I mean, a lot of what you call as practical questions will become relevant, but then you will have to forget that we are talking about some things that we understand. No, I am introducing you to a method. We will do blindly some of these alleys, we will go to the alleys, we will follow through the process, and hopefully we understand a little bit about that. The energy that you have here, H psi is equal to E psi, that E represents the only outcomes in an experiment for determining the total energy of the system. Whenever you make a measurement on the total energy of the system, the only possible values that you will get are given by this E. Energy is not the only measurable quantity. You have momentum, particles velocity, angular momentum if the particle is moving around about a point or moving about a line, the electric and magnetic properties of say molecules for example, the molecular structure, what is the size and shape and the bond lengths and bond angles, all these things are important and all these things are what we call as experimental quantities. Now the next strange thing that we have in quantum mechanics is, this is the third strange thing. The first one was that we will have to solve the Schrodinger equation. The second strange thing is that the momentum is given by an operator. The third strange thing is that, sorry, this should be the fourth one. The third strange thing was that the wave function does not have a meaning, but the absolute square of the wave function represents a probability density, or the absolute square of the wave function in a small interval of space gives you the probability of finding the system in that space. That is a third strange thing. And then the fourth strange thing is that what do we get when we make a measurement of properties of the system. We do many measurements and we try to get an average. Quantum mechanics gives an expression for the average value. The average value for any measurement of the quantity represented by A is given by the integral psi star A psi d tau by the integral psi star psi d tau. For example, if A is the momentum P in the x direction for example, then it is psi star, you recall, minus I h bar d by dx, that is the operator associated with P psi d tau divided by the integral psi star psi d tau. So the fourth strange thing is that every measurable quantity in quantum mechanics is represented by an operator, the momentum by the differential operator as one of the earlier ones, likewise dipole moment, bond length, bond angle, electric susceptibility, molecular polarizabilities, many properties are there. Every such experimentally measurable property is represented by an operator in quantum mechanics, and if the wave function of the system is given by psi, or if the wave function of the molecule is given by psi, then the measurement of that property on an average will give you the results as given by this formula, psi star operator psi star psi d tau. So go back and see that the prescription is that. Prescription for measurement processes is that on the average what we will get for measurement of properties of the system. So these are all the things that we will come back again and again and again. Okay. So let us just see what we can do for the rest of this lecture. How do we go about trying to make sense out of these four strange quantities? We will understand, or we will try to follow this by four simple model problems. Okay. We will study a few simple model problems. The problems can be solved mathematically exactly, so that you will get functions, analytic forms for the algebraic, for the wave functions and so on, and then we will try and become familiar with the process of how to solve the Schrodinger equation for various systems. What are the various systems? We will have four models. The first model is the most elementary model called the particle in a box. This is the simplest Schrodinger equation that you can solve, one dimensional system. The second is a particle moving in a ring, slightly more complicated. An even more complicated system is the harmonic oscillator. we will try and solve these things using the Schrodinger mechanics, the biomechanics, and then of course the hydrogen atom. The chemists, the starting point of chemistry, the quantum mechanics in chemistry is the hydrogen atom, the lightest and the first in the periodic table, simplest atom, one electron system, one electron, one proton. You would see that the quantum mechanics of the hydrogen atom is quite difficult, okay? And you have already seen qualitatively the solutions of the hydrogen atom in terms of orbitals in your high school, wave functions, orbitals, the orbital diagrams and so on. The present method is to give you some of these pictures in a little more quantitative manner, and the orbitals of hydrogen atom are extremely important for chemists because they form the basis. The methods of solving the Schrodinger equation for hydrogen atom form the basis for understanding molecules. Therefore, I will spend a considerable amount of time in the analysis of the hydrogen atom through the methods of quantum chemistry. Why do we solve these problems for a chemistry course? We do this because we want to understand what is meant by the statement that molecules have discrete energy levels. These are responsible for the transformations that the molecules undergo. We want to understand the process of formation of molecules. We want to understand how the molecules get excited by light, laser light for example, or any other microwave radiation, and eventually the chemical transformation itself, why molecules undergo transformations, why some molecules are unstable, the others are very stable, why molecules rearrange, all these processes, the chemical transformation processes at the atomic level. If you want to understand, we have to study some of these model problems. Okay. Let me go with a quick summary. We will elaborate the following models. The first one is a particle in a box. I am going to write the Hamiltonian without any explanation now, and in each one of the subsequent lectures I will explain the model, the box problem. For a particle moving inside a box in one dimension, if we call this as the coordinate, and we imagine that the box is of length L such that the walls of the box are infinitely steep, meaning that the particle can never escape the box, it can only move inside the box, and inside the box the particle is free, there is no potential energy. You remember that the Hamiltonian is kinetic energy plus the potential energy. Therefore, if the particle is moving inside the box and if it does not have any potential energy, obviously the Hamiltonian is given by its kinetic energy. The particle cannot escape the box, and the mathematical condition which imposes that is that the potentials at the ends of the box, the two ends, are infinite and positive, that is steep, repulsive. The model for this, the Hamiltonian, is given by the equation minus h bar square by 2m d square by dx square plus v, where v is 0 if x is between 0 and L, okay, which we write by saying v is equal to 0 for x between 0 and L, okay, and v is infinity otherwise. Therefore, we want to solve this equation or this operator h. What is the equation that we want to solve? The equation we want to solve is, with this h the differential equation H psi of x function of x is equal to E times psi of x, and this is a constant. We want to find out psi of x and the energy E. This is one model, the simplest model. And that is what you see in the slide here. The Schrodinger equation for a particle in a box is minus h bar square by 2m d square psi x by dx square plus v of psi is equal to E times psi, where v is 0 for the particle inside the box and is infinity otherwise. This is one model. The second is, of course, instead of a one dimensional motion, we can have a rectangular box and we can think about the particle moving in 2 dimensions or in 3 dimensions or in n dimensions. Therefore, how do we generalize this? The Schrodinger equation for a particle in a 2 dimensional box, we have 2 coordinates x and y, and therefore the wave function psi is a function of the coordinates x and y, and you see that this form is very similar to the one dimensional form, minus h bar square by 2m dou square by dou x square. Now it is a partial derivative because you have 2 coordinate variables, and dou square by dou y square. This whole term minus h bar square by 2m, this represents the kinetic energy of the particle and the wave function psi, and the potential energy of the particle V, the left hand side is all the Hamiltonian acting on the wave function, is equal to E times the wave function. Again it is a h psi is equal to E psi. What are the conditions? The conditions are very similar. Here we are talking about a square box of x also between 0 to L, the same length, and y between 0 to L. So for a square box the potential is 0 inside the box and it is infinity otherwise. This is the second model we will do. The third model we would study is the Schrodinger equation for the harmonic oscillator. The harmonic oscillator has a potential energy half kx square if x is the amplitude of the harmonic motion and k is the force constant of the harmonic oscillator system. Okay. This comes from your classical physics, the potential energy for a harmonic oscillator. The kinetic energy for the harmonic oscillator is p square by 2m, and that in quantum mechanics is now replaced by the derivative expression minus h bar square by 2m d square by dx square. Therefore the potential energy plus the kinetic energy acting on the wave function psi. Therefore again what you have is a h psi is equal to E psi. Now the values of x in this problem for harmonic system is in mathematical conditions x can take any value from minus infinity to plus infinity. That is a model we would solve. And the last is of course the most important one for the chemists, namely the Schrodinger equation for the electron in the hydrogen atom. The Bohr model, if you recall, you are used to drawing a circle with the electron on the circle and the proton in the middle, and drawing the potential energy as the Coulombic interaction energy of the negatively charged electron and the positively charged proton. You recall that if the distance between the two is r, if you draw, this is not a circle, but let us imagine this to be a circle. Okay. If the electron is on the circle and if this is a proton, and if this interaction, if this distance is r, you know the proton has a charge plus Ze, the electron has the charge minus E. Okay. Z is 1 for a proton, for other nuclei Z depends on the number of protons you have. What is the Coulombic energy of attraction between these two electrically charged particles? It is minus Ze square by 4 pi epsilon naught r in classical electrodynamics in the SI units. You must have remembered this from your electromagnetism in high school. So this is the Coulombic attraction, but the electron is of course not stationary. You remember from the Bohr model that it is moving around, and the Bohr model introduces something like a planetary motion for the electrons. Bohr's picture is also quantum mechanical in the sense that he was able to explain the line spectra of hydrogen atom through this planetary model. Now we have the Schrodinger equation for the solution of the hydrogen atom, which is hopefully much more general than the solution to the hydrogen atom that Bohr proposed, and the potential energy for the hydrogen atom system is minus Ze square by 4 pi epsilon naught r. What is the kinetic energy? The kinetic energy is p square by 2m again, but now P is that since the electron is moving around in a 3-dimensional sphere with the proton in the middle, the momentum has 3 components in a 3-dimensional world, the x, y, z component, and those components are written in such a way that you have the kinetic energy of the system given by the 3 momentum p square by 2m minus h bar square by dou x square minus h bar square times dou square by dou y square. This is px square, this is py square, this is pz square by 2m. Now that is the kinetic energy expression in quantum mechanics. This is the potential energy, because you know the distance r is given in terms of the distance from the origin. If the origin is at the center of the nucleus, then it is minus Ze square by r square, Ze square by r. What did I write here earlier? Yeah, I wrote only r minus Ze square by r. So what you have is the potential energy is that the potential energy given by minus Ze square by this. So h times psi is equal to E times psi. These are the model problems that we will study before we move on to molecules. So let me summarize this lecture. What we did was, why do we need quantum mechanics in chemistry? We went through some explanations. I wouldn't call it something that you would understand, but hopefully this will make sense over a period of time. And then an elementary introduction to the principles of quantum mechanics without any explanation that these are the rules, now you will play by the rules, and you will understand them by playing the game by understanding the rules. And then the introduction to simple models. We will continue with this with the particle in a box in the next lecture. Thank you.